thanks very much. So Azure SQL Ledger, has anybody heard of it? Do you know it? Anybody used it, turned it on, had a play around with it? No. Okay. So I've used it only in terms of figuring out how it works. I haven't used it in a production app yet. It's still in public preview on Azure, and it's coming to SQL Server 2022. I seen about a 30-second video highlight of it at Microsoft Ignite last year. Thought that looked useful, didn't understand what they were doing, so went and had a look at some of the other demos. And it's really just going to run through some of these demos tonight. Hopefully by the end of the session, you'll know what it does, how it does it, and be able to decide if it's useful for you. So, old problem here. We just need to capture the history of any data changes. So that's the super easy part. If you've never heard of a trigger, you'll be able to create a trigger 15-20 minutes on Google and have it push some data into a history table, and happy days, you've got your history. The last bit then in red is the tricky bit. Convince the auditors the data hasn't been tampered with, and that's a lot more difficult. So two methods of tampering. The first just be some unauthorized person running some queries against your tables. So if you're copying something into your history table, can someone get access to it and just change the data in it? The second method of tampering is a bit more devious. So if you can imagine, you take the backup, you get the main data file of your database, restore it into a database somewhere where you are an administrator, change it there, create some disaster, and force the DBA team to restore your backup for you, and slip your changes in that way, or just directly edit the MDF with some kind of text editor. So not necessarily an easy thing to do, but two different ways to be tampered. So if I jump to the next slide, this is my agenda then. So the first thing I'm going to look at is just why triggers are not the answer, or maybe why triggers are not the answer on their own. There are loads of people doing this with triggers, but they'll inherently have to have something else added on top, because triggers in SQL Server on their own are super easy to hack. Then I'm going to do the actual demo of SQL Ledger. So we'll create and update a table, and then verify it. And having had a quick look at why triggers are not the answer, you should be able to see pretty readily the difference between the triggers and Ledger. At that point, if you didn't really care how it worked, you could just stop, you could use it, but I'm going to explain how it works. And we'll have to look at something called hashing and what Ledger calls digests. There's a couple more little things you have to consider, and then finally I'll show you how to turn it on in the portal. It'll make more sense when you know how it works as to what we're actually turning on in the portal, but the portal is super easy to use. So I'm going to jump to Management Studio. I'm going to spend most of the time in Management Studio. So this is about why triggers are not the answer. So I've got two tables here, compliance status history. I've got a little trigger on them. So if I add a couple of rows, you'll see what's happening with the history table. Totally standard stuff. So now two rows in here, myself and some other person called David, and the trigger has automatically populated our history table down below. So we're moving from having nothing to a status of not started. Then someone comes along, an authorized person, and updates David's status. So David is now done his training, that's great. And his status changed to completed, and we've got an extra row here in the history table. So all totally standard, normal stuff. So if you're not familiar with triggers, super easy to hack, you just turn them off. So disable the trigger, and then now I can start to mess with the history table. So I'll change the status for me to completed. I'll steal David's entry in the history table so that it looks like it was me, and I'll move David back to not started so that I'll cover my own tracks. Turn the trigger back on, and whoever comes along next will not know that anything happened. So if I now look in the compliance table, you can see that it now says that James has completed, David hasn't started his, and we've got a date and a time here when James did his training. So the data's been completely tampered with, and all you need is someone who's got the right permissions. So you'll probably end up with something where your developers aren't allowed production access, or you have to do your deployments through a pipeline so that you can't tamper with your data. But what are you going to do with your DBAs or your sysadmins who've got permission to do anything they want on the database? Plus, triggers give you no protection for the other tamper method where you're forcing a restore of a backup. So what's different with Ledger? So it's, on the face of it, it looks pretty similar. And again, this is one of the demos that is in Microsoft's own, their own steps. So I'm going to create a schema, I'm going to create a ledger table. You'll see here the bit of syntax down the bottom. We've got to turn versioning on, and then we've got this extra ledger equals on. So nothing terribly unusual seems at that point. What you will notice now is if I refresh these tables, we should see the table that I created, account.balance. Okay, so here it is, account.balance. And it depends on which version of Management Studio you're in, but in this version it appears as a child within the hierarchy. So we've actually got another table here called account ledger history, and then we've got this number on the end. So the number is just the object ID of the original table. Yeah, 644. So if I query these two tables, the top one is the table I created, and the bottom one is the history table that Azure created that's going to make up the ledger. I'll add a row just to make it easier, so I've got some data in it. So I've added myself in there. I've said I've got a balance of 200, and now I'm going to change my balance to 300. So if we look at these two rows again, so the top one is the table I created, and the bottom one is the history table. So we're here with the 300, so that's the final value I had. So I started at 200, went to 300. So my table shows that I've got a 300, and the history is saying the 200 here. And you've got these transaction IDs where this starts and where this ends. We'll get to those transaction IDs and what they're all about in a minute. If you want the full history, including the up to date, then we'd have to write a query that combines these original table and the history table. But Azure have done it for us, and they've given us a view. So they've created a view in here as well when I created the original table. So it's in here, account.balance ledger. So if we query this view, it's a lot easier just to understand what's going on. So you'll find that you probably never actually used the history table, you just used the view. So now we've got the full history here of what's happened. So the first transaction here, 1307, that was the insert. So that was the first insert that I created, where it was 200. And then we've got two rows in the history table, which is what I did for the update. So Ledger treats an update as a delete and an insert. And it shows the insert first, but you're not getting any primary key violation because there never was an insert or a delete. There was just an update, I ran an update. But in terms of how Ledger reports it, it shows it as an insert and as a delete. These two things are both sitting here with the same transaction ID, so they're both in there as 1310. Now, what's totally different here compared to the trigger approach is I can't update this history table. So even if I try and I'm sysadmin on this instance, it kicks back and says this is a Ledger history table and you can't update it. So that pretty much prevents the attack from a high permission user and going in and changing something. Doesn't matter if you're sysadmin, you can't change it. I'll add in a couple more people just so that we have some more data to play with. And now if we query it, the last thing I want to look at is this table, database ledger transactions. So if I create that, or have a look at that. Okay, so the main use of this is to combine these transaction IDs. So the last update I made to my own, where I changed it to 200, or from 200 to 300, was this transaction in here, 1310, and then we just did a lookup here. So 1310 was done at this commit time, and it was done by this person. So if anyone comes in here and does try to change it or does try to tamper with it, you've got a history. Again, you can't update that sys table, you can't update the history table, so you've got a tamper-proof solution in terms of who made the changes and when. And that's great. Again, I've got the extra one here. If I now change it and do actually change it to 500, we'll see that it was me that did it again. So I'm going to get caught. And that's great, but it still leaves this other problem in terms of tamper of well, what if somebody can get at the backup file and make a change there and then restore it. So within Ledger, Microsoft have given us this piece of code. If we run this, it comes back and tells us verification succeeded. So this is Microsoft telling us that nobody's got to your MDF file, messed about with it, and restored it back into your database. So if you trusted it, you could just leave it at that. But if you want to understand how this verification worked, then we need to talk about the actual verification process, which is just the next thing I was going to run into. So if I jump to this next slide. Okay, so this is the flow of the tables we've got so far. So we started with the ledger table, which I created on the left, and then Azure created the history table and the ledger view. So while we've been doing those inserts, Azure has been taking snapshots of something, pushing them into a trusted storage area, which I don't have access to and can't change. And then when we ask it to do the verification, it compares the values that are sitting on the database with the values that are sitting in trusted storage. And if they match, then it says that it's been verified. So if someone was to have hacked the MDF file, changed the values around, redone the restore, and then we do the verification, they'll see that no, something has changed. The values that were put into trusted storage are different. From what you had on the database, your verification has failed. So the question then comes to, well, what is Azure storing in trusted storage to do the verification against? So I've got some options here, some sort of replication, backups, transaction logs, whatever. And none of these are good. What they want is something small, something that's easy to transport, something fast. And as well as that, if we actually had another copy of the data in another place, it would be another place for it to get lost from. So what they've actually used is hashes. So before I talk too much about that, I just want to describe what a hash is in case someone hasn't seen them before. So if we jump back here and have a look at hashes, so the hash batch function in SQL Server, this is using the SHA algorithm. Ledger uses a 256-bit one. It just converts any string into some kind of code down here. So these are deterministic, so if I run them multiple times, you get the same thing each time, and they're one way. So the meetup is on the 24th, will always be turned into this, but it's virtually impossible for me to turn this back into the string. So this hash of the string is a way of representing the string. And this is what is being saved off in the trusted storage. It's these hashes. So I've got a quick demo of how this works. So I've created a table here. Let's view the table. Okay, so I've got the 3 in here. I'm just going to create the hash. Okay, so we've now hashed these 3 strings, and the next step is I'm going to tie them together in a chain just by hashing one into the other. So, and that's just going to be my hash to the previous. So if I do that, simple queries, let's have a look at the table now. So these 3 here in the row hash are the hash of the string. Then the hash to the previous for the first one, I just set it equal to the first one because there's nothing else to hash it to. Then for this one, it's the hash of this one plus this one, and this one is the hash of this one plus this one. So this final hash is a function of these 3 hashes, or the hash of these 3 strings, but it's also representative of the order that they're put in because they've been hashed to each other. So this one hash represents, if these were all done in the same transaction, one whole transaction. And if something was to change in these 3, and then we recalculated the hashes, we'd expect this final value to change. So I think I've got this here. So this is the final value. And if I just change something and rehash it, we should see that it changes. So I've now changed it from 6 to 630. Recalculate the hashes. Okay, and that final hash is different from the first time I calculated it. So if I originally had this value somewhere in trusted storage, and then I recalculate all my hashes, get to the end and I see that they're different, I know that the data has been tampered with. And that's really the principle that it's working on. I don't know specifically what's changed. There's no way I can take this hash or take this final hash, work backwards and figure out what the data is. So it's not about identifying what's changed, it's about saying whether or not it has changed. So it allows you to say, and I know the data hasn't been changed because. If the verification fails, you don't know why it failed, you just know that it failed. Okay, so haven't seen that hashes. If we look once more at this table that we've looked at briefly before, which is the ledger transactions, you see what's happening here is this column here. So the column is table hashes, but these are effectively hashes for this transaction. So everything that happened in that transaction gets hashed together and becomes this table hash. And the same for the next transaction and the next transaction and the next transaction. So from the PowerPoint, I can just talk about how that happens. So this screenshot, the piece on the left, is from Microsoft's documentation. So inside the transaction, you could have multiple rows being created. One of the ones I did had 2 rows, the other just had 1. But up to n rows, and what actually gets hashed together then is all of these things on the bottom. So the number of columns, the first column name, some metadata about it and its actual value. And that is repeated for every single column, and all of those are hashed together as one giant string. And that's done for the first row, so that's hash 1. Same thing happens for the next row, it gives us hash 2, 3, 4, and so on. So all of the individual rows get hashed to form a hash for that row. Then the hash of the first row and the second row are combined together, the third and the fourth combined together, and so on and so forth. And the process repeats until you get down to just one hash. So that's called the root hash of the transaction, and that's what gets stored in the table hash column in Database Ledger transactions. So that root hash is basically the same as what I did in my demo with the 3 rows, where the final hash you identify it was changed. So in the same for this, if this has 1,000,000 rows in it, we'll have 1,000,000 hashes at the first tier, then 500,000 and so on in the hierarchy, till we get down to 1. And if we recalculate the hashes, if we change one row, recalculate all the hashes, the root hash will be different. So in theory we could save these table hashes off the trusted storage, but it's not what Microsoft do. They take it one more step and they do this block hashing. So this is a pretty busy slide. The left hand side again is the database ledger transactions. So we've got the hashes here for each of the transactions. What it does then, it defines a block as a 30-second window, and any transactions that are inside that 30-second window are all hashed together to form a block hash. So in the same way as previously for transaction hashes, we were hashing the rows to form a transaction hash, now we're hashing the transactions to form a block hash. So the first block will only have one row, or only has one row. You can see the next block had 4 transactions in it, and they're all inside a 30-second window. So those 4 transaction hashes or table hashes get hashed together to form the block hash, and that's repeated here. We've got 4 different blocks, and then it also says here the block size. So that's just the number of transactions. You can see it's 1, 4, 3, and 5. And then the final thing that we do here is the same as I did. We hash them back to the previous. So again, for block 0, it's showing that it doesn't actually have a block hash to the previous. That's fine. But then for block 1, it's being hashed the 0 and the 1 together to give us this. And then block 2 is hashing the hash for 1 along with the hash for 3 or for 2, and so on and so forth. So you now have a block hash that's hashed to the previous block hash, and that forms a chain, or if you wanted to call it a blockchain, you could. These block hashes are called digests in Azure SQL Ledger, and they're what actually gets sent to trusted storage. So the only thing that gets sent to trusted storage is every 30 seconds you have one hash, which is super small, so you have very low I/O. So the next slide just talks for the full flow for verification. So same as before, we've got the updatable ledger table, the history table, and the view. The history table and the view were created by Azure. The only thing I created was the ledger table. Then we've got two sys tables here for the transaction hash and the block hashes. As the block hashes get created every 30 seconds, they get sent as digests to trusted storage. Then when we kick off the verification in this dash box, the database engine has to recalculate all of the row hashes, turn those back into transaction hashes, and then redo the block hashing. So we now have a new version of the block hashes and the transaction hashes, and then the verification process checks the block hashes stored on the database with the ones that are sitting in Azure. And if they match, then that's a guarantee that nobody has changed any of these three tables, either getting at your master data file or finding some other way to hack it. Okay, and that's it. That's how it works. The last few things I've got here. Okay, so Ledger can be added when you're creating a new database, or it can be added to an existing one. I'll show you in a second how to add it to a brand new one. But it's basically the same process. And once it's there, you'll see this little box in the blade in the portal for Ledger, and you turn it on in there. It's about 3 clicks, super easy. We also have the option to create append-only tables. So the one I showed was an updatable table. So you got insert, update, and delete on it. You can also create an append-only table. The syntax is slightly different. You can't have system versioning on, and you have this append-only equals on added in. With an append-only table, you can only insert, so there's no need for a history table because the table itself is the history table. With the updatable tables, then you need the history table to tell you if things have been changed or deleted. If you use the updatable tables, then you don't need to rebuild your application, so you can use it on an application that's already built and live. If you want to switch over to append-only, you may need to change your application design. The last thing then is performance. So generally, creating and saving the digests is considered to be fast if you read the documentation. There's some overhead in doing the hashing, and there's some overhead in populating the history table. But if you were going to use a trigger, you'd have overhead running and executing your trigger. Running the verification process can be slow, because every single row and every single transaction has to be rehashed, then rehashed together to form the transaction hash and back into the block hash. In terms of how slow is slow, I put about 1 million rows into a table and ran it on the super cheap 5 DPU instance of Azure SQL, and it took about 30 seconds. I ran the same verification, scaled it up to 2 cores, and it ran in about 3 seconds. So those sorts of numbers, but potentially if you need to do it, scale your machine way up. The documentation suggests that verification is not something you're going to be running on a daily basis. If you are, you've probably got other problems. Why do you need to run it on a daily basis? It's the sort of thing that you run periodically every 6 months to convince yourself that everything's working fine, or that you run it when the auditor comes in, or when you've got an application where there's some other party that doesn't trust you and wants to verify that you're not lying to them. Okay, I think the last thing I want to do then is jump into the portal and just show you how to turn it on. Okay, so this is the server that I've created for this demo. So if we go to create database, .id, okay, and it's back. Right, so we're going to create the database inside the server. Have to give it a name. Anything will do. 2 cores will do for the demo. Don't need storage. On the networking, don't need anything in here. Right, so if you get to this section where it says Ledger, and it's still in preview, I don't know when it's going in general release, we click Configure Ledger, and we get one screen, and that's it. 2 boxes to choose from. The top one, if we click this, then every single table in the database will force to be an updatable Ledger table, which may be what you want, may not be what you want. I think most databases I've worked in probably not what you want, because you'll end up with some tables that you don't care if they get changed, something that's login, something that you clear down on a daily basis, something that's staged. There's no value in having that as a Ledger table. All you're doing is just increasing the length of time to do your verification. So if you don't click this, then you can have updatable Ledger tables, append Ledger tables, or tables that are nothing to do with Ledger. So leaving this on tick gives you the more variety. The last thing that we do have to do then is configure the digest storage. If we don't configure this, then you've got nothing stored, so you can't do the verification. But it's super easy to turn on. One click, and then we've got two choices, Azure Storage or Confidential Ledger. So we can use our own storage account, and then you're responsible for making sure that that storage account is secure. If you don't want to have that hassle, you pick Confidential Ledger and Microsoft takes care of it. It's in the documentation that Microsoft can't actually get to this themselves. Whether you trust them or not is up to you. The Confidential Ledger then, I've already got one created. If you don't, you click Create New, put in the name and pick a region. There's only 3 regions at the moment which you can pick from. It's in preview. Once you've set those, click Apply and you're done. And it'll go off and create it. That's it. Those are all the options you've got for turning on Ledger. If you're trying to turn it on one that already exists, a database that already exists that isn't ledgerable, I don't have one at the moment, but if you just look up one that's in here that already has it turned on, you'll see you get the same little thing here on the blade that says Ledger. And you go in here and you can't, if the database already exists, you can't force to make everything ledgerable, because you can't go back and create a history table for your tables that are already populated. So that option is grayed out for you, and the only things you've got to turn on then is where you're going to create your digest. So it's pretty much the same whether you do it before the database gets created or at creation time. The only difference is if your database is already created, you lose this option to force it. That brings me to the end. I was told it was alright to do a plug. Boo. Yeah, so Deloitte are hiring. I picked these yesterday off that website. So if you know anybody who's interested in anything kind of architecturally on Azure or on-prem as well, any kind of data engineering stuff, you can have a look on the website. I have to dash unfortunately after this, but Sam and Rachel are here from Deloitte as well. So if you want to chat to them about what's going on at Deloitte, you can give them a shout. That's it for me. I can take a few questions, though I haven't used it a huge amount, so I'm slightly nervous about asking the questions. Go for it.
So I know
Right.
this is not because Microsoft.
Agree. Okay, so it's not blocked.
Can you repeat the question just so that we recording gets?
Yeah, sure. So you're pointing out that this is not blockchain because Microsoft own the technology. The ledger exists only in one place. It's not distributed. Other people can't download the entire ledger and look at all of the details because Microsoft own it. Correct. So it's not a blockchain. If you read the documentation of Microsoft, what they said is they worked with a bunch of companies that were building blockchain solutions. And more often than not, what they wanted wasn't, well, what they wanted was some way of saying, and now we know the data hasn't been changed, it hasn't been tampered with. So when they put in the amount of effort that they did to get blockchain solutions up and running, there were a big number of problems with them. The amount of effort, the work, other solutions, when the blockchain was created, how do you query the blockchain? All of that stuff. Okay, let's take the blockchain and put it into a database to query it because we can't query it directly because that's too slow. And now you lose all the security of what it was a blockchain to start with, why we put it in a database to query it. Now we can tamper it. So the benefit of this over a blockchain is this is super light. You don't have to build. You don't have to know what a blockchain is for a start. You can just use it. You don't have to build the blockchain technology around it, and you can be sure that it hasn't been tampered with. Now, if you make the case that Microsoft own the technology and own the hardware, and there aren't any other copies anywhere else, so Microsoft could be lying to us. True, they could, but if you don't trust Microsoft to store your blockchain or to store your data, you shouldn't put it there to start with. So. A DB that no one has access to, may as well turn it off. Yeah, but if, like,
Kind of is what confidential ledger is.
yeah.
It's the same thing.
No, but it has a lot of extra benefits. If you have a database that you said okay, so you say create a database that's read only. It's not read only for your sysadmin. It can't be.
I don't know why Microsoft tried to sell something from maybe when they're
I think they're not trying to sell something blockchainy. They're trying to find. Yeah, absolutely. But what they're saying is, I mean, I don't work for Microsoft. I don't care. Use Oracle if you want. Yeah, I trust Microsoft. I mean, if you don't trust Microsoft, then you just don't use Azure. You know, you go and find something more secure, right? That's the problem, right? So, you'll say, someone will say, blockchain's more secure because I've got it on 40 different nodes. I would agree. I think Microsoft would agree as well. What they're saying is, this is something that sits on a SQL Server database on Azure that's super easy to use, super light, don't need to know what a blockchain is, and it's massively more secure than using triggers and some rules where you tell auditors, yeah, but our developers don't have access, don't have higher permission access, and we trust our DBAs and we trust our sysadmins because, you know, they're honest people and we did a security check on them. You know, that's garbage, right? So what they're saying is, Ledger is one option, one step. Have a think about it, see if it works for you. If it doesn't, use a blockchain. Yes. Yes. So if it was changed through a non-query mean, so if you had means to you know, get the database backup, restore the backup someplace else, change it someplace else, or whether you just took your main database file and edited it with some kind of editor, and hacked it that way and restored it back in. So that now that, you know, one row in this history table says something different, when you recalculate all the hashes, they would now be different on the database. So whenever you do the comparison to the version that you saved at the time you created them, they're going to show up as different, and it's going to tell you the difference. Yeah. Yeah, you're going to get caught. Yeah, and there's no way that you know, once Ledger has caught you and put you in the history table, you can't change the history table. So it doesn't matter what access you've got. You can't update the history table. It won't let you. But if you find a way of hacking it so that it did, then you would get caught when you do the verification. You know, well, by design, it won't let you. You know, if there's a vulnerability somewhere and someone manages to do it, then you'll get caught. You'll still get caught when the verification process runs. Cool. Is that us? I shall leave it to you.